e click in Stats.
Thank you, Anderson. I'm sharing my screen.
Yes, you are.
Right. Thank you, Robertino. Okay. So today we learn about a very important abstraction in Haskell that is also considered by most that learn Haskell like the biggest hurdle in learning it. So once you get through this lecture and understand it, then you're good to go, and then nothing will ever be able to shock you again. And that's the infamous monad concept of monads, so-called monads. And I think originally that term comes from philosophy, from Leibniz. I'm not sure. But I mean, it's like specific to Haskell. Or actually, it's not. I mean, these days, other languages embrace it as well. I just yesterday or so, somebody showed me a functional programming library for TypeScript, and they also had something like monads. And you do get monads in Scala, and you do get monads in F#. Only there they are called workflows because they didn't want to scare people off. But it's a very powerful feature. But I mean, some beginners or learners of Haskell find it difficult. So, I mean, it's a joke that basically every Haskell person writes at least one monad tutorial in his life. So there are like lots of efforts to make teaching that easier or understanding that. So I hope we'll do okay with this lecture. And so the goal is to introduce monad, which is another type class. I mean, we talked about type classes, I mean, a lot of them, but in particular, we talked about functor and foldable. So monad is like of the same kind somehow. So it's for type constructors like functor or foldable. We also, if we have time, talk about applicative, which is a bit weaker than monad. So actually the hierarchy is functor, applicative, monad. But historically, monads were discovered first, and then only later people discovered that there's something sitting between functor and monad, which is also very useful in its own right. So that's much more modern. Okay, but I mean, at the beginning, we won't do anything new. We will just look at things we already know how to do and just look at them from a particular angle. And so the first step is to revisit maybe. And just recall that we have this maybe type. So that's like for optional values, that where there may be an A or not. So if there's no A, we call it nothing. And if there is an A, we wrap that A with the just constructor. And often maybe is used as return type of functions that can fail. So when other languages, in imperative languages, you might return null or throw an exception. In Haskell, we often like indicate the same thing, that there's a potential for failure with maybe. So for example, looking up, given an A, I mean, we had this table type. So this is, I think this is also called property lists in Lisp, for example. So lists of pairs of A and B. So you can think of A as keys and B of values. So it's like poor man's map or hash map or whatever. And then given a key of type A, you can try to find a pair where the first component is that given A and then return the B. But of course that can fail because maybe that key can't be found in the list. And we can turn that into a pure function, a total function that will never crash by giving this the maybe return type. So if such an A is found in the list, then the corresponding B is returned with just. And if no such A is in the list, then we just return nothing. And similar, there is in the data.list module from the base libraries, there's this find function. I think lookup actually is also there, but find is, I think, more commonly used. So given a predicate on A's and a list of A's, this find function will scan the list. And if it finds an A where this predicate is true, then it will return just that A. And if no such A exists, then it will return nothing. So maybe I can demonstrate that. And in order to do that, let me just go to our course lecture thing. Kenya 94. Samples Haskell. Good. We close all this old stuff. Let me open the container, same that you are using. Have to wait until the container is initialized, but that should hopefully not take very long. Right. Okay, good. Yeah, just where I closed these testing files, I said we should also talk about test coverage. And maybe you can do that at the end. And now I'm in full swing of talking about monads. So let's see. So there's this abstraction pattern folders. Let's change into that. And open a REPL. Right, I'm not sure. Maybe I should just let's see. I'm not sure whether I should just create a new module. But let's go with this one until I find a problem. So ignore these imports. It's not important. Okay. Right. So let's just demonstrate this find function. So if I import data.list, then I have this find function in scope. And here we see it's even more general than indicated on the slide. So on the slides, we specialized it to lists of A's, but it actually works for arbitrary foldable containers. But we can just use it for lists. So for example, we could use find even 320. Yeah, I mean 299 is also fine. So this looks for the first even number in this list of ints. And it finds the 4. So it returns just 4. So there is an even number in there. The first one of those is 4, and so it returns that. If I give a predicate that isn't satisfied, for example, greater 500, then it returns nothing. Okay, so that's the maybe type for you. I mean, we have seen that before often. And okay, so on the slides, it just says that assume that we have a data structure with the following operations: up, down, and right, from location to maybe location. And just see, just a second. Trying to understand that. I mean, that's sort of because this is abstract. Trying to understand what this update thing does. Right. I mean, we could think of, I mean, let's make that concrete. So maybe, I mean, we can think of, I mean, moving around on some grid, let's say. So location could be, I mean, you can think of a game, for example. So like a simple two-dimensional game where the player walks on a grid. and you can, for some reason, not walk left, so you can only walk up, down, or right. But it can fail, maybe because there's a wall. And I mean, if you are at like the top and there's a wall, you can't go up and so on. And this update, I mean, we can think that maybe these locations contain some sort of data as well. So it's like a, I mean, maybe the coordinates and some number, and then you can update this number. So let's just try to make that concrete. So we could say data location let's say log x, the x coordinate, and log y is the y coordinate, and then I don't know, log v for value. Okay. And now let's say we have this up log to maybe log so let's say that so I don't know, I mean, you can decide, of course, how the grid is oriented, but let's say it's like in mathematics. So it I mean, the origin, let's say, is at the left lower corner of the screen. So x goes upwards from left to right, and y goes upwards from bottom to top, like a graph you draw in mathematics. And let's say the thing, I mean, the grid only has, I don't know, 10. I mean, the highest, I mean, it's just from 0 to 9, let's say. Let's say it's from 0 to 9, 0 to 9. So it's like this 10 by 10 square, right? So the point is, I can only move up if my y coordinate is not 9. I mean, if it's 9 or higher, then I can't move up. So I mean, we can use record syntax actually to do this. So, but we don't have to, of course. But let's say, I mean, L for log. So we check whether the log y of L is less than 9. And in that case, we can move up. So what do we want to do? We don't change the x coordinate. We want to increase the y coordinate by 1, and we leave the v coordinate alone. So if you recall, we talked about record update syntax. So this is useful in this case. So I can take the original L, and now I basically make a copy of that. So I don't modify. I mean, in Haskell, we very rarely modify existing data. We always like create new one. So I leave the L, I mean, create a copy and leave the x and y as it is. And I just change the log y to log y plus 1. Why is this giving me? Sorry, and I need a maybe type, so I must wrap that in a just constructor. Okay. And here I forgot the L. Right, and in the other case, otherwise, it's nothing. So if I'm already at the top of the grid, I can't do anything. Just an example. Okay, now we need, what was it, down and right. So let me just copy that. So down is easy. So it's just that instead of I must be less than 9, now I must be greater than 0. And in that case, I can go down and decrease the y coordinate. And that's called down. And finally, right. So now I must look at the x coordinate and see that that is, I mean, it's up to me, but let's also say, sorry, less than 9. And now I update the y coordinate and increase it by 1. Okay, so now I have those things. And there was this update function. So let's have that operate on this v value. So update. So update function and the location. I use record syntax, record update syntax again, and I leave X and Y alone, and I just apply my function f to the old value of v. Okay, and we can try this out. So for example, we move up from, I mean, I could write it like this, which would be clearer. So let's say I'm at 3, 5, 42. Then that succeeds, and my x coordinate doesn't change, the value doesn't change, but the y coordinate increases by 1. If, however, I'm already at 9 here, then that fails. And I mean, I can walk down. So instead of 5, I'm now at y coordinate 4. And of course, if I'm already at 0, that fails. And I can also go right. So now the x coordinate increased by 1. But if I'm already at 9, that fails. And finally, I can update with some function that operates on the v. So for example, I can do times 2. And now the x and y coordinates don't change, but the v is doubled in this example. Okay, so far so good. And that's nothing new, of course. I mean, we have, especially also in the assignments, have used functions with maybe all the time. So that's like an old hat. Right. But now let's say that we want to do something like this. So we want to go up, right, and down, and then update with +1. So let's say go up, right, down, then update with +1. Is it called? No, it's not called anything. Let's call it foo. So from location to maybe location. Okay, so we start with a L1. Okay, so first let's do up. And up can, of course, because it has a maybe type, it can succeed or fail. So so we must check, and we can, for example, use the case construct. So if up L1 fails, I mean, then we already fail with the first step and can't do anything else. Can't move any further. But it could succeed, so we end up at a new location L2. And now we can go right. So again, this can succeed or fail. So we apply this right function to L2. And now again, this moving right can fail, in which case we are done. We can't go on and the whole thing fails. But it could succeed, and we end up at a third location L3, in which case now we can try to walk down. But with this again can fail, in which case we are stuck. But if it succeeds, we end up at the fourth location, L4, and then we can apply our update, this +1. So then just update +1 L4. So, I mean, we can try this out, for example, again with this example look. Sorry, with this one, for example. Right. Let's do this foo. So let's see. So in this case, it worked. So we started at 3.5. So we walked up, got us to 3.6. Then we walked right, 4.6. Then we walked down, 4.5. And then we incremented the 42 to 43. So that succeeded. But if somewhere on the way we get stuck, so for example, if our X location is 9, then it will be nothing. I mean, the first step will succeed. We can go up, but then when we try to go right, we'll run into the wall and it returns nothing and stops there. Or of course, if we started already at the top, it will also fail because the first step already fails this going up. Okay, and again, I mean, there's nothing new here. I mean, we have seen maybe before, we have seen the case statement before, so nothing new. But if you look at the code, then, I mean, first of all, it looks ugly because it has this increasing indentation. And Haskellers don't like that. I mean, that's a code smell in Haskell if you have something like this. And secondly, what Haskellers also don't like is this repetition, because we are using the same thing over and over again. So we make a case statement on a maybe, and then if the result is nothing, we return nothing. And if the result is just, then we continue. So let me just check the right. I'm not sure I want to do it like, let me just check at the imports. No. And so the point is, there are like, I mean, what are these things? I mean, what we want to do is this. Yeah. The third question, I mean, the third problem, I mean, so the first problem is just optical, that we, like, it's this dangling right ladder. Second problem is like typing. I mean, I get carpal tunnel by just looking at this. And the third one is also, it somehow obscures the meaning of this code. I mean, basically this comment is very succinct. I mean, go up, write down, then update. With the understanding that each of these steps can fail. But like this, I mean, this going up, write down, I mean, it's still in there, but it's like hidden behind a lot of noise. So when a Haskell sees something like that, we always try to abstract away the pattern. Find the pattern and abstract it. So what we really want to do is, I mean, we want to sequence a couple of steps where each of those steps can fail. And if the steps fails, then the whole thing fails. But if it doesn't fail, we continue with the value we got. And I'm not sure in the slides, it's called bind. I think I should maybe just call it bind and not this operator. Or I can also let me remove this stuff. I mean, we had this sure. I do this. Yeah. We had this operator before in the second to last lecture when we talked about I/O, and now we want to, and in I/O it was used to sequence I/O actions, if you recall. So this was the most powerful operator that allowed us to do one side effecting operation action and then sequence it with another one. But I want to use the same operator now in this case. And so what we, I mean, if we look at this long enough, then hopefully we see that we have something of type maybe A, like this up L1 or right L2 or down L3. And we have a way to, if this succeeds, if it's not nothing, to continue from there. So if that succeeds and we really get an A, we can do a second thing. And overall, we have something that potentially gives us a B. but it can fail. It can fail here or it can fail here, in which case we get a nothing. So we can implement that basically just looking at this pattern. So if the first thing already fails, then we don't care what the next step would have been because the first step already failed. So we just end up with nothing. However, if the first step succeeded and we have a way to go on, and that is often called cont for continuation, which is just fancy for how to proceed, then we can take this A and apply our continuation to that A. Okay, and so that compiles, I think. I mean, the editor says it does. I can also, now I get all sorts of errors. Let me just remove all that crap. Not sure what I actually, probably I hit the wrong thing. Let me just check. Sorry, T. Right, I want to hide that from Prelude, sorry. Okay, now I shouldn't get this warning, and okay, fine. Right. And somehow I'm a bit, sorry, let me do this differently. I mean, the organization, let me just copy this and call it maybe. And I just have to, in the Cabal file, introduce this now. I'm sorry, I sometimes always do that spontaneously different each time I teach this. I think it's better maybe in this case to do it separately. Okay. Did I do now?
The comma.
Oh, yes. Thanks, Robertino.
Also, I think you're running low on battery, maybe?
That's very likely, yes. I didn't see the pop-up. Charging my phone. Okay. Thank you. Okay. So all good. Right. And then now, of course, we want to use this. So my claim is that with this abstraction here, we can write this nicer. So let me just copy this. And now, I don't know, I could call it bar or foo prime. So same thing, same idea, but now I want to use this new operator I defined. So where hopefully I can avoid this repetition. And now I can use this. So I can use my up L1 and now use this new operator here. And I call the result L2 if it exists. Now this boilerplate goes away. Now I have, sorry. So now I do the going right. And I can again use this. I mean, this can succeed or fail. So I can again use this new operator I defined. And the potential result, if it doesn't fail, is L3. This boilerplate again goes away. And now I do the L3, and I can use my cool new thing one last time. Call this L4. And this also goes away. This is now all expressed in this pattern. Sorry, and now I can do this. let's see. And let me just, there was this example here, the old one. And if I now use the new one, then I get exactly the same result. So this code does the same as this one, but arguably it's much nicer. And there's one other thing. I mean, here, this was dealing with computations that could fail. So what I'm doing here is, how do I sequence? I have a computation that can fail, and afterwards I want to do another computation that can fail. And this here basically says, okay, if the first one didn't fail and I get a result of type A out, what do I do next? And this operator allows me to sequence these two things together. And this boilerplate with the case and in the nothing case I immediately fail is now encoded in this operator. So I had to define this once, but now I can get rid of all this boilerplate 3 times and do this. Now there's one other thing we can do. Here's this just. And this is, of course, I mean, we could also say, okay, in this case, I mean, update does not fail. So update is something that is guaranteed to work. So we can define a second thing that we call pure. A2 maybe A. The pure is just. And we could replace this with pure. I mean, it's just another name. But basically to indicate, I mean, we are talking here about computations that can fail. They can succeed with a just, or they can fail with a nothing. And if I have two such computations, I can chain them together. And the logic is, if the first one already fails, then the whole thing fails. But if the first one succeeds, I take the result of the first one and then try the second thing. So this is like, the idea is, now we're dealing with computations that can fail, and we encode them with nothing. I mean, maybe, with maybe. But then, of course, there are also computations that never fail, like this update. And we want to have a way to see computations that never fail as computations that potentially can fail. So we just never make use of that potential. And I call that pure. And now if I reload and ask for pure, then it says it clashes with something from the prelude. So let me hide that as well. What now? 43. Yeah, okay. Okay, and I can try this thing again, that foo and bar obviously still give the same result. I mean, all I did was give another name to just. Okay, and also notice that this code almost looks like you would write it. I mean, imagine you are doing, I don't know what your favorite programming language until you heard about Haskell was. Let's say Python or TypeScript or something. I mean, a typical imperative programming language, maybe this up, right, down is just implemented with throwing exceptions or returning null. And then you could just, I mean, in Python or JavaScript or something, you could just basically write something like up L1 or L2 equals up L1. Sorry, I'm not sure. Maybe like, yeah, no, it was okay. Better before. And then you can do L3 equals, or assigned to right L2. And 4 is down L3. And then maybe something like return whatever, I mean, update on F4. I mean, this looks very similar. I mean, there's some noise here with this this new operator, but it's very similar to something you would write in a programming language more familiar with you. And of course, each of these steps here could crash. if you hit a wall. But then you maybe would just throw an exception, and as soon as an exception happens in one of those steps, the whole thing throws an exception. The behavior here is very, very similar. I mean, we don't use exceptions, but as soon as one of these intermediate steps is nothing, the whole thing is nothing. If we hit a wall somewhere on the way, the whole result is nothing. And so it's just like it looks almost imperative. I mean, Haskell is a functional language. We don't do it. I mean, we don't have statements, and I mean, I should actually add semicolons. Very important. Right. And in in an imperative language like Python or so, the semicolon, I mean, would basically mean you chain these things, these statements, these commands, and each time there can be an exception. And if somewhere an exception happens, then the whole thing crashes. But if not, then basically you just go on. So the logic here is somehow continue while you don't get an exception. But if one of those statements throws an exception, then the whole thing throws an exception. And in principle, we did exactly the same thing here. So, I mean, again, the behavior is exactly the same. So we try all these steps, and if at each step it succeeds, we get an overall result. But if one of those steps fails, then the whole thing fails. And also note that what I complained about earlier, I mean, this ugliness that it slants to the right, this is gone. Now we can format it nicely like this. I don't have to type so much. So it's only 4 lines versus 1, 2, 3, 4, 5, 6, 7 before. And so I avoid all this repetition and boilerplate. And the logic is also much clearer. I mean, here's still some fog. I mean, this looks a bit ugly maybe. But if you concentrate on the left, this is now much closer to the comment, what I actually want to do. So it's much clearer. I mean, even if you don't worry too much about this operator, if you just think of it like a way of the semicolon here. So if you blend this block here out, basically, I mean, I can't highlight this, but I mean, if you blend this out, the thing on the right here, and only look at this, I mean, the first, the up, the right, the down, then it looks very much like this comment. So it's a very concise way in principle to describe what I want to do. And the behavior that all of these things can fail, and that if one of those fails, the whole thing fails, is encapsulated in this operator here. This is exactly the logic. So here I define that. Okay, are there any questions to this?
Not in the chat.
Okay, so now let me copy this and call it either. And let me reload. Okay, so now if you think of this thing as exceptions, I mean like a Haskell version of exceptions, so then nothing indicates something went wrong. If you compare that to exceptions in other languages, then it gives you less information. I mean, exception often tells you what went wrong. Here we just know, I mean, if we get nothing, we just know something went wrong, but we don't know what went wrong. So it would be nicer if we could somehow also, I mean, like with exceptions, if we could also not just know that it didn't work, but if we also got an indication why it didn't work. And in Haskell, for that purpose, instead of maybe, we often use either. So this log type says exactly the same, but we, instead of maybe, we use either, and then, I mean, either is AB, has two type parameters. And should, I mean, in principle, it's completely symmetric. So there's no, I mean, left and right, I mean, the left and the right are completely symmetrical. But traditionally, if you want to use either for something like this, where one value can indicate success and the other can indicate failure, then traditionally the left one is used for the failure case. And I mean, there's a nice, what's the word in German? It's Eselsbrücke. Rule of, I mean, it's easy to remember because, I mean, left and right is right. So the good case is the right case. And basically now for the first type argument, that's, you can think of that as the type of error messages. So that could be anything. It could be a special, I mean, we could define a special error case for this. I'm not sure whether I should do that. Why not? Maybe. Or it could just be string. Let's go with string maybe. So for example, like this. So now the idea of either is, I mean, of this, I mean, I replace maybe with either string. And the idea is where earlier I just gave nothing if it failed. Now I can use the left constructor of either to give an error message of type string. And instead of string, I could use, I mean, I could also define a new type. Maybe I can do that in the second step. Right. So now, of course, if I do this, then, sorry, whatever I did. If I do this now, then it won't compile anymore because, I mean, I'm using either now, but so just doesn't make any sense anymore. And for some reason, I don't get, why don't I get red squiggles everywhere? Just reload this thing. What was that, Robertino, you said the other day? If I don't want to rebuild the container and just reload, what can I do?
You can open the command palette, and
Yes.
if you type Haskell language server or HLS, it will prompt you. Yeah.
Okay. So hopefully it will work now. Yes. Okay. Now lots of red squiggles. Okay. So the good case is still the same. So, I mean, if I don't run into a wall, except that now I, of course, can't use the just constructor anymore. That's for maybe. Now I must use the right constructor. And nothing also doesn't work anymore. I mean, now I must use the left constructor in this case, but now I have the additional luxury that I can give an error message. So that can be whatever I like. So for example, I mean, I could say, I mean, I can, whatever.
Out of bounds?
Yes, I was wondering whether I should get some context information. I mean, I could say, for example, can't go up from show L. If you allow me to just, I mean, just, as I already said in the very first lecture, I mean, now I had lots of red squiggles, and that's bad. So one should always try to keep everything compiled. So now I commented everything out so that at least this first thing should compile. Otherwise, it's difficult to see what's going on. So now if I go back to my earlier examples, where I at some point went up here, here. So now it's, I mean, I get the same result as before. So X and V stay the same, but Y is increased. The only difference is that instead of just, it now says right. But if now I have a 9 here, I mean, earlier we just got nothing, and now I get a left, can't go up from this location, which is arguably nicer. I mean, we get more information about what went wrong. So now let me fix this. I mean, do the others. So, I mean, it's the same. I mean, I must replace the just with right everywhere. Why is this now an error? Because of course I must also replace these with either string and this as well. And now here I can give another error message. For example, can't go down from OL. I must replace just with right and nothing with another message. can't go right from L, sorry. Right, and the update can stay exactly the same. Okay, and now I can try the same example. This food thing. Go up, right, down, then update. But now with this richer type. And earlier I had to pattern match and decide between, look at nothing or just. Now with using either, I have left or right. So I can have left arrow. So what do I do in that case where I can't continue? I've errored out. So the obvious thing to do is to just pass this error along and stop at that point. But if I get a right, I can continue. And then, so I try the second thing, going right, and again, it can error out. In which case, there's nothing I can do. Or it doesn't error out. Sorry. In which case, I can continue. And again, this step can also fail. In which case, the whole thing fails. Or it can succeed. In which case, the whole thing succeeds. And now, as before, I can test it. So if I start somewhere in the middle of my grid, then the whole thing succeeds and I get the same result as before, except now I have a right constructor here because I'm in the either type and not a just. So walking up turns that to 6, then right turns that to a 4, and down turns that to a 5 again, and then incrementing this 42 to a 43. But now if I, for example, start very close to the right wall, then it says can't go right from location 9, 6. So here we see, we first tried to walk up and that succeeded. So from 9, 5, we went to 9, 6. And then we try to go right and we get this error. But if, for example, I immediately start like at the top, then I get a different error message that I can't go up from this location. So earlier with these examples, I just got nothing. And if you think you are responsible for somehow figuring out what went wrong, then in the earlier case, all you got was that something went wrong, but no additional information. But now there's at least this error message which gives you a clue. But again, we have the same comments that I made before. It's ugly because it leans to the right. There's a lot of clutter. I repeat myself over and over again. I pattern match on this either. In the left arrow case, I return left arrow. I do that 3 times. And in the right case, I take the result I got and run with that. So exactly the same we did before, we can do again. We can introduce an operator that we can also call bind. But but now for either. So instead of maybe we now have either string, either string, either string. And now, of course, instead of nothing, we have left arrow. We don't care what we wanted to do next because we can't do anything next anyway. We just return this error. And now instead of just, we have right. And in that case, we do want to continue with our continuation, and we just apply the continuation to the value we have. And here, this pure, if I turn that. So now the good case, the case where nothing can go wrong. Earlier it was just, now it's right. Now it's right. So this compiles. And now the very cool thing is, if I remove this and turn that into either string. Somewhere I must have, yeah, sorry, I had this. So why do I get all these? Okay, whatever. Ignore these. Just wonder why I didn't get them earlier. But anyway, that's just hints. I wonder whether I can switch them off. It's a bit irritating. Yes. You can also, I mean, these hints, you can switch them off with this hlint pragma. Right. I mean, these blue squiggles are just suggestions. I mean, I think especially for you as beginners, they are very useful. So you should probably almost always follow them. But I mean, you don't have to. And sometimes they are just not good. Anyway. I mean, this is really cool, don't you think? That, I mean, the exact same code. All I did was I changed the type here. And now the exact same code works again. I mean, I didn't change a single character in the implementation. The exact same code works again. And but now basically, so it looks exactly the same, but it behaves differently. Earlier in our maybe version, I mean, because now we have these error messages. So the way you can think of it is that this bind is now, I mean, the bind now we have slightly differently. Earlier, we only had the case that something went wrong or not. And if something went wrong, we just, I mean, the whole thing goes wrong, but we have no additional information. Now it's slightly different. Now we don't only know that something went wrong, we know something went wrong with an error message. So if that happens somewhere, we immediately stop the computation, but we keep this error message. So that's this line here. And if it went right, we continue with the value we got. So somehow this glue between the steps, I mean, we want to do these steps in sequence, and we glue them together with this operator. And this operator tells us, I mean, what exactly that means, how to sequence these things, sequence things that can go wrong. It's very similar to the maybe case. So in the maybe case, it could fail or not. Now it can fail with an error message or not. So this glue looks very similar, but it's slightly different. But all this behavior with the error message, how to deal with error messages, is now hidden in this operator. And we can write exactly the same code, but we do get different behavior. So, I mean, for example, if we had this code already, it would be very easy. I mean, let's start, we started with maybe, and we had this code. And then at some point we get annoyed because we never know what went wrong. Then we can easily switch to this either type. All we have to do is basically change this operator here. And the old code we had still works, but it behaves slightly different now. Oh yeah, there's one thing that I can do. Let me go back to maybe. I mean, if you think of exceptions, I mean, I should hide this. Now I get the blue squiggles here as well. So let me just ignore this. One thing you sometimes want to do with exceptions is you want to catch them. So, and I mean, normally, we saw this already when we talked about I/O. So I mean, first of all, we can throw them and we can catch them. So, I mean, if we think of maybe, then basically throwing an exception means we just get I mean, no matter what result type was expected, we can just always do nothing. And we can also catch an exception. So what would the type be? Well, we try a computation. We want an A, but that can fail. So if it fails, we say what to do in that case. I think we have had that before. We called it, I don't know what we called it. But we have had that when we talked about maybe. So basically the idea is try this, but if it fails, do that instead. So if the if the first thing succeeds, or if it fails, if it fails, then we just do the handler thing. And if the first thing succeeds, we don't care about the handler, we succeed, or we could say pure A. Okay, and if we have this, I mean, we can, if you like, replace this with throw everywhere. Not everywhere, but let's say there. And now we could, for example, also use our handler. So we could do something like try to go up, right, down, then update with +1. But if it fails, do or whatever, I don't know, update with -1. And now we could, let's call that bus. Now we could use our bar. I mean, we can use our catch. So bus L1 is now, so we catch exceptions that happen in bar L1. And if it fails, instead we do update -2 L1. Why does that fail? Pure. That's this annoying thing in Haskell. The unary minus operator is somehow a pain. Do it like this. Oh, I said -1, sorry. That's fine. So now if we look at our examples again, so this succeeds, so bus will have the same result. Sorry. So this succeeded anyway. So our catch won't have an effect and we get the same result. But now earlier where we crashed because, for example, going right gets us into a wall. Now instead our exception handler catches that exception, and instead we stay where we are and decrease the value. And I can do the same thing here. Now. Let me just copy this, sorry. Just copy that and let's see what that looks like in the either case. So now we don't just, we don't just say something went wrong, we want to specify what went wrong. So we want to be able to throw an exception. I didn't really use, oh yeah, sorry, I can do that now. So this is just left. And now the handling. So we have something that can go wrong. And we have a handler. So now the handler can depend on the error message. Depending on what error we get, we could do different things. So now how would that work? So now it's not nothing anymore, it's left error. And we have this handler. So now we can apply the handler, which is now a function from error message to, so we can apply the handler to the error message. And if all went well, we don't need to handle anything and we just do, what I should call it B now. What's the problem now? I'm a bit confused. What did I do? Oh, I mean, first of all, I could use, that's a problem. I didn't do it for arbitrary either. I did it for string error messages. And now it should be fine. And this is string. Sorry. Okay, and now this bus. Okay, now I need this handler must be now take the error message, but in this case, I don't care about the error message. So I can just ignore that. Okay, and if I reload, so if I do the bar from a location where everything is fine, as before, I get the same result. I move and increase. But now if I do this when I'm standing to the right wall, I mean, without the exception handler, I get a left. But now if I use the bus, then it succeeds. I stay where I am and decrease by 1. Okay. So I think, are there any questions? And maybe we should have a break now and then we look at another example that's different. Other questions?
No, they are not questions. And maybe I think it's fine that you use either string, because maybe then we can say, okay, but maybe we can use other things that they are not string as errors, and it's easier to go from less general to more general, I think.
Yes, yes. I mean, I could use either AB afterwards. Okay.
Yes.
Okay, let's have
Yeah.
25 maybe.
Okay.
Yes.
Okay. Thank you. Talk to you then. Bye. Okay, let's continue. Or are there any questions?
Not in the chat.
Okay. Okay. I just spontaneously decided to maybe do something different to the slides and use writer as an example. Yeah, let me think. Right. Yes. Yes, I think I'll do that. Why not be spontaneous? So let me copy this again. Okay.
And you're not sharing the.
Oh yeah, thanks. I didn't do much. I just created a new module that I called writer. What is that? Okay. So let's try this out. What Robertino said. Language server, or must I say Haskell language server?
Yes, try Haskell. Yeah, there you go. Restart Haskell is.
Okay, great. Okay, now different thing. Let's forget about things that can fail. Let's say our room is infinitely large now and there are no vaults. But let's say that we want to somehow log what we are doing. And so the idea is, so nothing can fail, but we always want to like give an explanation of what we were actually doing. Let's say just as a string, or let's say as a list of strings. Okay, so now, I mean, this error case, we don't care. I mean, we can always go up. So there's no case distinction anymore. Sorry, I deleted the wrong one. That was the error case. Right, so we always want to go up, so it will never fail, but we want to somehow keep track of what we did. So if we go up, then so the result will be this new location, but I mean, we just say that we went up like this. Okay. And same for here, for down. I think it's the other way around, isn't it? I forget. The message comes first. Doesn't matter, I suppose. No, it should come first. I think. It's not really important at this point, but I think it will be. Otherwise, it's not a functor. Right. So I say what I was doing and I give a new location. So okay, in this case, I say down and I update my location. And for right, the same thing. Update doesn't. No, I suppose we can. Yeah, whatever. Okay. And so that's fine. And now let's do this. And the point now is I want to, I mean, each of these single steps gives me like some description, but now I want to keep track of all these, let's call them log messages. Okay. So let me just think briefly. In principle, I can do it the same way. So, okay, so this up now, I mean, there are no longer two cases, but there is, I mean, now I have this message one from doing the first step, or I mean, it could be messages. It's a list of strings. So let's call it, I don't know, access one. Um, right, and now I do, so the error cases don't exist anymore, but now each step can give me new log messages. Okay, and in the end, I want to somehow concatenate all of them. So I end up with this. Why? Oh, the right. What did I do wrong here? Oh yeah, the result type, of course, it's not either a string anymore. It's now this thing. Okay. And I mean, if I write it like this, so it's again, I mean, it's not as, maybe not as extreme as in the first two examples with maybe in either, but it's still annoying and repetitive. So in each of these steps, so I mean, earlier I had functions that could fail. So now my functions can't fail anymore, but they can produce log output. And now I have like a different type of boilerplate. So each time I have to collect these log outputs and I have to collect all of them and concatenate them. Okay. And I mean, at this point, I can, of course, try it. Let me reload. Open that and try it. So as I said, now nothing can go wrong anymore. So I can do foo. I mean, I can take one of my old examples. Doesn't really matter. Now there are no vaults anymore. Okay, and now I get like this nice sequence of log messages up, right, down, and the updated location and so on. So that works. But I mean, it's a bit tedious. So each time I do something that could produce a log message, I must basically keep track of this log message and then in the end somehow, I mean, concatenate them. So we can do the same idea that we did before. I'm defining such an operator here. Now, of course, so let's say the types have changed. So if I have something that can, a first step that can produce log output, and a second step that takes the result of the first and can by itself produce more log output, then I want to combine those two steps to one that can produce a potentially longer log output. I don't have the error case. So now I have like the first step produces access and some result. So failing is not an option. Failure is not an option. So what do I do in this case? Well, I mean, I apply my continuation to the result I got in the first case. Now I get more log output and the result of type B. And what do? I collect the logs from the first run, I mean, from the first step with the logs from the second step and concatenate them and return the B as overall result. Now this pure thing, so pure always means we have some sort of special thing going on with our computations. So in the case of maybe, the special thing was that they could fail without reason, with nothing. In the case of either, the special thing was they could fail with an error message. Now we are looking at computations that can not fail, but they can produce log output. And the pure was always for the case that this special feature did not happen. So the pure for maybe means we won't get a nothing, we will get a just. The pure for either meant we won't get a left error message, we will get a right. And the pure in this case means we could produce log messages, but we didn't. So that means we get an empty list of logs and just our result. Okay, and now I can write this nicer. And oh miracle of miracles, the same code that I used before still works. So nothing red. I mean, I can reload. I can also, I mean, this was this foo, and if I now do bar, I get the same result. So it's the exact same code I used for the first two examples with maybe and either, and it still compiles. I mean, the type has changed and the definition of this operator changed, but the syntax, the code, the characters on the screen are exactly the same as before. And what has changed is, like, again, this behavior, this gluing of sequences. So in the maybe example, the glue meant, okay, I mean, you have two steps you want to do. And this operator, what it did was it does the first step, it tries the first step. If the first step fails, it doesn't even just returns, immediately stops. In the second example with the either, again, we try the first step, and if there's an error message, we stop the whole thing and return this error message. If it succeeded, we succeed with the second step. Now in this example with the log messages, there's no trying. I mean, it will always work, but the first step can produce log messages. So we do the first step, remember the log messages from the first step. Then we do the second step, remember the log messages from the second step, and then we combine those, we concatenate those log messages. But the same code is still working. So it's still what I said earlier. I mean, it's very concise. So we know what we want to do, up, right, down. It's just that, I mean, there can be certain, let's call them side effects. It's not side effects in the same sense as in the lecture on I/O, not real world side effects, but it's something like muddy computation. So they don't just compute pure values, they have some other flavor. So in the case of maybe and either, it was the flavor that something could go wrong, they could fail. In this case now, they can produce like a log output. So we have these tainted side effectly computations, and this bind operator that we define, which depends very much on the types. So it's always been different from maybe either, and now this pair type. That may be completely different, but it has the same purpose, to do several steps in sequence. And the operator tells us how to combine two steps to one bigger step. Right. In this case, we don't have something like catch. I mean, this has nothing to do with errors now. So I should remove this. But there's something, I mean, so for failure, I mean, like there were these two special operations that we can throw exceptions and that we can catch exceptions. We don't have anything like that now. I mean, we look at potentially failure, I mean, at logging, but we could make that explicit. We could have something that traditionally is called tell, given, let's say, a string. This is maybe not completely correct. I should say a list of strings. That doesn't produce a result, but just logs. and not producing a result, I indicate with the unit type. And the definition is, of course, very simple. So this is basically like a log statement in, or a console log statement in JavaScript. And with this tail thing, I can write my things a bit nicer. I mean, this was a bit ugly. So oh yeah, and one last thing, I can, sorry, let me also hide from the prelude this sequence operator. Remember from IO, this, sorry, yeah, this one was very similar to that one, but it forgets the result of the first operation. So it does the first IO action and then the second, and ignores the result of the first. And as in IO, also here we can implement this one in terms of that one. So we can say, okay. So we have two of these log producing things. And we forget the sorry, I can just write that in terms of the bind if I want to. So I can say it's, sorry, I should do it like this. So I can say I do the first thing and then I bind, but I don't care about the result and just then do the second thing. And I can, of course, express that as const. And if you remember, that's exactly the same definition we also had in the IO lecture for this. Okay, and with that, I can write this much nicer, in particular when I combine it with pure. So now I can say tell up and then pure and this result here. So I lock and then I do this. I can also, yeah. And of course I can do the same stuff here. And the order also doesn't matter. I could also, I mean, I could first do the pure thing and then lock. Okay, almost there. Why is this happening to me? Why do I get an error here? Oh, because I forgot the pure.
Pure.
Yeah, thanks, Karina. Right. And everything else is fine. Okay. Okay. I mean, this doesn't change anything. It just makes it a bit nicer. So now I basically have isolated the side effects, the logging from my pure computation. And this is also very much as an, I mean, imperative languages. So you can just think of the log statement somewhere. I mean, if you debug JavaScript code, something goes wrong, then you can throw in a couple of console log statements to get an idea of what's going on. And this is now very similar to this. Okay, any questions to this?
Not the chat.
Okay, so now let's again, so now I mean, this is like completely different. I mean, the first two examples were about computations that can go wrong. They were very similar. The only difference was that in the either case, we have error messages. This is, I mean, completely different. It's computations that can't go wrong, but they can produce log output. But nevertheless, we see that with this bind operator and the pure, we can like write it very similarly. the effect, and the overall result, the location we eventually get out is the same in all cases, but the side effects like the logging now or the exceptions and so on, that's of course different between the examples. But we can write the exact same code, and all this, the treatment of this special stuff that can happen, like exceptions or logging, is encapsulated in this operator and the pure. Okay, so now let's look at something, yet another completely different example. State, but I think now I don't really see a good way to keep this log stuff. So I think now I switch to tree labeling. Let's call it state. Okay, let's call it state. And let's revisit our tree type. Tree A could be a leaf with an A, or it could be a node with 2 subtrees. Okay, and now I think that was also an assignment maybe, but anyway, let's look at labeling. So you have a tree, some arbitrary type A in the leaves, and we want to label it. So we want to have something label tree that takes such a tree and turns it into a tree of the same shape, but now at the leaves, instead of just A's, we have an int and an A. And the idea is it basically labels, it numbers the leaves from left to right. So the leftmost leaf is, let's say, 1 or 0, whatever. And the next one is 2, 3, 4, and so on. I'm always so tired of drawing trees, but I suppose we should have an example again. Let's say tree character. Okay, let's see. So let's say on the left, we just have a leaf with a capital Q. And on the right, let me use the dollar. That makes it a bit easier, I think. So at the right, we have a node. And there on the left, we have a node with 2 leaves. Let's say lowercase x and I don't know, a dollar sign. And on the right, we just have a leaf with a 4. Okay. Okay, I can show. Why not? Oh, let me reload the REPL. State. Okay, yes, obviously. Okay, we have our example tree, and now let me try to draw it. So we have the root. And on the left, we have this Q. On the right is another node. And there on the left, we have yet another node. On the right, we have the 4. And on the left, we have our X and dollar. Okay, and the idea of labeling now is that we turn this into the following. So the leftmost leaf is this one here. So we have a 1, Q there. And then the second leftmost is this X. So we have a 2, X here. And now the drawing becomes tough. So the next one is this one. So this is now not very nice. And the last one is this one. And of course, the 4 is actually a character. I mean, this is the character. I mean, the Q and the X and the dollar also have, should I? I'm not sure. Okay, 1, 2, 3, 4. Maybe I should call it, so that there's no confusion. Maybe I should have given a different, let's call it hash. Okay, so that's the task to do this. And how would you do that? And if we just basically start, if you have listened in the lecture, then the natural way to think would be, that we distinguish between the leaf and the node case. I don't know. Right, and then you could, I don't know, you could say this is leaf 1, A, but then sort of we are stuck here. If we do, the only thing we could do here would be label tree left and label tree right. This would compile, but if we now call it on our example tree, then obviously the result is wrong because all our leaves are labeled with a 1. So that doesn't work like that. So then if you think a bit about it, then the idea is that you probably need a helper function that gets like the first label to use. So let's call that label tree prime. So it's gets an int, which the idea is it's the first label to use. Sorry. What am I doing? Let's call that n. Let's worry about the implementation in a second. But then if we have this helper function, then the implementation is very simple. We can just say it's label tree start with 1. So label tree prime 1. Okay, so now how do we implement this label tree prime? And we see this also still doesn't help. Okay, we could start. So now instead of the 1, we would use the n here. And now in this case, we would call label tree prime start with n. Okay, we start with the left subtree with this label n we are supposed to start with. But what do we do here? What do we put here? With what label do we start here? In order to know this, we would need to know how many labels were needed to label the left child. And we don't know this here. So this also doesn't work. So what we need to do is, instead of just returning the tree, we must also return basically the, let's say, the next available label so that we can then start with. So in this case, and then we can use that here. So the idea is this argument gives us the first label to use by labeling this tree. and then the result will be the label tree and the next available label. And if we have this, then of course this doesn't compile anymore, because now we have this pair, but we are only interested in the label tree, so we can do, we just look at the second component. And now here, so this return type would be wrong. So somehow I get far too little squiggles. So let's do that again. Okay, now I get satisfyingly many squiggles. Okay, so in this case, what is, after I've labeled the leaf with n, what's the next available label? Well, obviously n plus 1. And now in this case, so what do? We label the left tree and somehow get this pair back. So let's say case label tree and left tree of, that's the pair with an, let's say n prime. So the new and labeled left tree. So then we can do labeling the right tree. So we label the right child, and now we know with which label to start, namely the n prime we got out of here. So we label the left tree, and this function tells us, okay, after labeling the left tree, the labeled left tree is L prime, and the next available label is n prime. So now I can label the right tree with starting with this n prime I got from the first computation here. And now I get an, let me call this n1. N1. Now I get, after labeling the right tree, n2 is the new available label, and I get the labeled right child. And now I can give the overall result. So after labeling left and right, so now the next free label is n2. So I can return the n2 here. And what is my labeled tree? Well, it's the left child labeled and the right child labeled. So this hopefully should work. Right, and now I hopefully get this. So Q gets label 1, the X gets label 2, the dollar gets label 3, and the hash gets label 4. Okay, so that works. Any questions to this?
Not immediate.
Okay. And this is also, I mean, it's not as extreme an example as what we saw before with this. I mean, it's not so obvious here, but we have again these, I mean, maybe if I write it like this, it's a bit more obvious. We again have like this dangling situation. I mean, as I said, it's not as dramatic as before, because I mean, earlier we did these 3 steps, up, right, down. Now it's basically only 2 things we need to do. I mean, in the node case, because we have to label the left and the right tree. But nevertheless, we have this thing again, like some sort of pattern. And in this case, the pattern is we are threading through state. You can think of this n as state. The basic, I mean, if you did this in JavaScript, you could define a mutable variable that is first initialized to 1, and that's like the next available label. And then if you encounter, I mean, maybe I could just do this. I mean, in JavaScript, it would be function. I mean, or let's say pseudo JavaScript or something. I mean, it would be something like this, right? You begin, you set, you have something like some variable n that initially you initialize to 1, and then I don't know how to, I mean, let's say we had a case in JavaScript which we don't, but so then we would distinguish and I don't know. Let's say function label tree p, something like this. Okay, and I mean this doesn't exist in JavaScript, but I don't want to bother with JSON and stuff now. I mean, it doesn't matter. We could say, okay, fine, why not? Let's say something like tag leaf. Then we would whatever t value, something like n and t value, so we can update it in place even, and we would increase the label, so because now the n is used, and in the other case, if it's a node, we would just call label tree on the left. Let's call it whatever, t left, and label tree t right. And I think that would more or less be valid JavaScript. Something like that. Okay. And so if we had a mutable variable like in JavaScript that always keeps track of the next available label, then we would just in the leaf case, after we have labeled our leaf, we would just in place increment that. I mean, mutate the value of n. And then this would work, sort of. I think we would need to define the var outside. Like this, whatever. But you get the idea, I hope. Now in Haskell, of course, we don't have mutable variables, or at least not really. So we can't mutate this. I mean, we can't do something like that in Haskell. So what we can do is to keep this around. So we keep the current value of n around, and we return the updated value. So instead of modifying it in place, we say, okay, this is the value for n you start with, and maybe whatever you do changes that, and we give the new value here. And now when we do like two things, we want to label the left tree and the right tree, we have to thread this state through the computation. So we do our first computation, we label the left tree, we may get a new, this n1 may be different now to the original n. And then we do our second step, and again, we may get an updated value of n. This is now n2. And then the overall computation has this one now, the state of the second step we did. And first of all, this is ugly, and you need to come up with lots of names. And again, it muddles. I mean, this is sort of much clearer than this. And there's also repetition again. I mean, the same pattern, we do it twice. And you also have to concentrate that you don't mix up things. I mean, this program would also compile if I made a mistake and wrote a N1 here. I mean, I would get this warning that I'm not using N2, but nevertheless, if I now do it, I mean, I get the wrong result, I hope. Yes. So it seems to work in the beginning for 1 and 2 and 3, but this hash again gets the 3. Right, so this is wrong. And the compiler, I mean, okay, fine, to be fair, it does warn me. That's why one should always take these warnings seriously, because often if you don't use a variable, and I mean, that hints that you did something wrong. But anyway, it would compile, and so this is like, it needs mental capacity from us that we would rather spent on other things. And it's very similar again. I mean, if you think of what I said, I mean, in the beginning we had computations that could fail and computations that could fail with error messages. And then we looked at computations that could log. And now we are looking at computations that have state and can modify state. And in Haskell, we model that with this. And before we go on, we can give a name to this. We call it state. I'm trying to think, should I do it polymorphic or, yeah, why not? So this is supposed to be a type of a computation with state S, mutable state S, and result A. So we do something that depends on the state S, and the computation can also modify the state. So let's call the new type constructor state, and let's call the accessor run state. Okay, and now we do exactly what we did here, this idea. So it takes the old state and it gives us a new state and a result of type A. Now, what we can do is we can rewrite our computation here in terms of the state thing. So we can say, instead of this, I mean, we could also swap these two arguments. I mean, it would be exactly the same if I instead write it like this. So I just swap the order of the arguments. Let's do that here as well, of course. Okay, that and here as well. So now I can't write it like this anymore. Or I could with flip if I wanted to. Can also do it like this. Okay, and now I did that because now, I mean, as I said many times before, the function error is right associative, so I could also think of these parentheses here. So using my new state type, I can also call this state, I mean, with a new type wrapper now, state. So the type of state is int, and we have tree. Sorry, I don't know. So it's state type int, tree, int, comma a. Right, and now I must write this a little bit differently. So given and label, because now I need this new type constructor. So this is exactly the same, and I must do this here as well. Okay, and here I must get to the, like this, this tuple again. So I must now unwrap it from the new type constructor. I must do run state n label tree L. From here. It's the other way around. Okay, and here again. So as we know, these U-type wrappers always muddle the water a bit because we have to always wrap and unwrap stuff. But with these minimal changes, that same code still compiles. And now I just have to throw in a run state here as well. So run state label tree prime t 1. And what's this now? Okay, let's ignore this. Okay, so now it looks even worse than before because of this state stuff. But now I have a type that I can actually, I mean, I could also, instead of new type, have used the type, but anyway. Right. But now it will get better because now we can use the same idea again. So I mean, the point is I have two stateful computations in this node case that I want to do. I want to label the left tree and the right tree. And in this context, now we can think of those as stateful computations, computations that modify state. In our example, the state that they modify is the next available label. If I label the left tree, I will need some of the labels, so that changes. If before I could start with level 5, maybe there are 3 leaves in the left subtree, so then I need the 5, the 6, and the 7, so my newly available label will be 8. So the state will have changed from 5 to 8 in this example. So, and I have 2 of these stateful computations that I need to perform, namely labeling the left tree and labeling the right tree. And that is very similar, if you think about it, to the other 3 examples we had, where we want to sequence 2 computations that can fail or 2 computations that can log. Okay, so obviously we will again define an operator. Again, same. So going from, we have one stateful computation and using the result of the first one, a second stateful computation. And we want to combine them to one big stateful computation. Okay, so we have our X and cont. Okay, so we want something of type state, so we need the state new type, and let's call the initial state S or S1. So what do we do? So we first execute the first stateful computation. So we run state, this first computation with our initial state S1. Okay, and what do we get? We get a new state and a result of type A. And now what do? We run state again. Now the second computation is the continuation applied to the first result. And now we start with state S2. And if you squint, then you can see that this is exactly what we did here. So we run the first thing in this example, labeling the left tree with our initial state N. We get a new state out, and then we run the next computation with the updated state from the first computation to get our final one. Okay, and in all these other cases, we also had pure, which was a computation that doesn't make use of these special features. So in the case of maybe or either, it was a computation that didn't fail. In the case of log, it was a computation that didn't log. And in the case of state, it's a computation that doesn't modify the state. So given a pure value of A, how can we turn this into a stateful computation? So we have an A, we want something of type state. So given an initial state, well, if it doesn't modify the state, the final state will be the same as the initial state, and the result will be our A. What's it complaining about now? Well, I could write it like that, but I don't want to. Okay. Right, and now let's revisit this and see whether we can using these this bind and return or pure, we can write it nicer. Okay, let's first not touch this. But now this one we can make nicer because we can say, let me move this. So what do? We first label, sorry, also double prime, label tree double prime our first, our left tree, and now we bind. The result will be L prime. Now we bind that to labeling our right subtree. The result we call R prime. And now finally we do pure node left prime right prime. And what is this? Didn't I hide? Oh, this time I deleted everything. Okay. Okay, it compiles. And now I can, instead of this label, I mean here, I can just also use the double prime. And hopefully the result is still the correct one for our example. And this looks now, I mean, the second case here, the node case, looks now identical more or less to my JavaScript example. I mean, the JavaScript example, I didn't even bother with the N. I mean, the N was handled implicitly here, and the interesting stuff was going on in the leaf case. And in the node case in JavaScript, I could just call it on the left tree and call it on the right tree. And this is now basically the same thing, or very similar. And again, like in our earlier examples, we have this clutter here on the right. But if we ignore that, it's now also much clearer what's going on. So in order to label the tree, I mean, if you label the leaf, you like smack the label on the leaf. But if you label a node, you just label the left tree and label the right tree, and that's it. And the handling, the threading of state between the left and the right is now implicitly hidden in this bind operator. Now we can, let's look at, I mean, recall that for maybe and either we had this throwing of exceptions and catching exceptions as like special operations that only apply for those cases where computations can fail. We didn't have that for our writer. For the writer, however, we had something else that was specific to that use case. If we want to consider computations that log, we introduced a special function combinator, whatever you want to call it, tell, that logs. So, I mean, is there a question?
Yes, I get a question. Could we just also write this example with the do notation?
Indeed, but we don't know that yet. But we will at the end of the lecture.
Oh, okay.
Very good question. Right. Special things. So I mean, if we looked at computation that could fail, then in the domain of failing computations, you would want to like trigger failures explicitly with throw, and you want to be able to catch them with catch. Now, a completely different domain is the domain of computations that can log stuff. So there you want like the special ability to emit a log message, and we call that tell. Now, what would be the analog for stateful computations? And I mean, if you look at, I mean, it's maybe not so clear, but from my JavaScript example, I mean, what we want to do is we want to be able to access the state, read it, and like here, we want to be able to update it or set it. So if we have mutable state, we want to be able to get the state, I mean, get the state out, the current state, and we want to be able to update it with a new state. And in Haskell, that's traditionally called get and put. So get is a stateful computation that as a result gets us the state. So the result type is the state type. And put takes a new value for the state and is a stateful computation that does not have a result, but updates the state. And we can easily implement that. So get, so we need our state constructor. Well, and if the current state is S, then I mean get is, the purpose of get is to get us the current state. So it's just given the current state, we return the current state. And of course, now my editor is complaining again because this is just the identity function. We can write it like this. And put, so if we want to put a new state, so state, so if our current state is S prime, we don't care about the current state because we want to update this state with this one, and we don't want to return a result. So now it's complaining that I don't use this old state, and now it's complaining that I can just as well use const. And why is this complaining? Ah, that was wrong, sorry. I mean, I keep the old state, I don't modify the state, but I return it as well. So like this. Okay, and with this, I can now also make this leave case nicer. So I can instead write, I mean, what do I do? I look up, I mean, what do I want to do in the leave case? I want to get my current state, so the next available label. I want to increment it, and I want to then return this thing. And I mean, this increment, so one other thing we can do, it's called traditionally modify. So if I, but I think, okay, there is that, but I think at this point we don't need it. So let's rewrite this label thing with this new way. So using get and put, what I can do is I get. So I get the current label out. I put. So I increase the label with 1. I don't get an interesting result. Why? And now I can return the result, which is leave with this label I looked up and the A. Right, and if you recall in the tail, I mean in the writer example, I also defined this, which said I'm not interested in the result of the first computation. I can do the exact same thing here. So given 2 stateful computations, I want to do both. That can sort of modify the state, but I don't care about the result of the first. And again, I can do exactly the same definition that I did with the other 2, or the other one. And if I do that, then I can write this here a little bit nicer, this part here, because this step, the put step, doesn't give me any useful result, so I don't need to why is this now not working? Okay. So this even nicer. So basically look up n, update the state with n+1, and emit the, or as a result, it's the leaf labeled with the n I looked up. Okay, and then it looks almost like this JavaScript thing. I mean, we could also, yeah, fine. It looks like this JavaScript thing. And we don't have to, I mean, as I said here, we can make mistakes. I mean, we have to thread through, so it's clutter. It muddles the water. It's not so clear what we do. I mean, it's not so clear that in this case, we just first label the left tree and then the right. I mean, because of all this noise. And we can make mistakes somehow, instead of N2 writing N1 here. And now all this clutter is again hidden in this bind operator. And we have these special things, get and put, that only make sense for stateful computations. They wouldn't make sense for maybe or either for operations that fail, computations that can fail. For those other special things make sense, like throw or catch, or for the writer tell. So now we have, I mean, now hopefully we have seen, and okay. And now let's also think of IO. I mean, obviously, I mean, it's the same operator. So there we were looking at computations that can have side effects in the real world. And we also had this bind operator that can sequence them, or I mean, bind two of them together, glue them together. And in the case of IO, what the bind operator did was, I mean, it takes two of these plans, or it takes, I mean, a plan and a continuation, and then it creates a more complex plan that first performs the real world side effects of the first one, gets a result out, applies the continuation to the result, has more real world side effects, and the result is a big plan with all those side effects combined and the result of the second computation. In the case of maybe and either, we can glue together two computations that can fail. It's not IO, it's not side effects in the real world, but nevertheless, we have computations that are like have this special flavor, namely the flavor of being fallible. And with our bind operator, we can glue two such things together. And the bind operator handles the special treatment in this case. Namely, if the first one already fails, we don't even bother with the second one, it immediately stops. With or without error message in the case of maybe and either. In tail, we have two computations that can produce log outputs. I mean, writer, and we can glue them together by collecting the log outputs from both and combining them, concatenating them. In the case of state, we have two computations that can modify state, and we combine them by threading the state through. So first we start with the initial state, then do the first computation. It can update the state, and then we do the second computation with this updated state and get a third state that may again have been updated and the result of the second computation. Also, in all of these cases, we had this pure. So we have these special feature of our computations. They can fail, they can log, they can have state. And the pure was always for computations that don't make use of the special feature. So they don't fail, they don't log, or they don't modify state. And the same we also had in the IO lecture. So we also had pure or return, which is like a potentially real world side effect having computation that doesn't have any real world side effects. And now hopefully you have seen enough examples to spot the pattern. So the idea is we have a type of computations in some sense. So you can think of it as computations with side effects. And then we have this bind operator, which takes two of these things, or rather one and a continuation that can, given the result of the first, produce another computation of this kind and glue those two together, bind them together. And how that bind works depends on what side effect we are talking about. The bind, I mean, the definition, the implementation of this operator here was completely different for the various examples I looked at. So this is like specific to the use case I'm looking at. But the idea is in all cases to bind two computations with specific side effects together. And we always had this pure, which produces a computation that doesn't have any side effects. And we had these special things that very much depend. I mean, this is not common for the examples, but for all the examples, we had like special help, I mean, special useful functions that were specific for this case. Throw and catch for failing, tell for logging, get and put for state. And for IO, we had these primitives like get line, put string line, read file, write file, whatever. And some genius, I don't know, maybe Phil Wotler, at some point realized that, I mean, that there is this common thread that a lot of things like side effecty things have this pattern that you can somehow, that there's a good sense of gluing them together and combining two more complex ones. So then when you have something like that, then, I mean, as a Haskell, you always think of type classes. So that's where, I mean, a new type class was born. And now I'm actually not really sure how to, okay. So now basically the idea would be just, okay, and that for whatever reason, this type class is called monad. So this, I mean, after what we do, I mean, know now, this would be class monad, type constructor. It's traditionally called M. And we have two operations, bind. So given one computation with result A and a computation, a continuation, we can glue those two together to get an MB. And the second, or first, whatever, called pure, type A to MA. And why do I get all sorts of, right. Okay, and now, of course, we could obviously make all our examples an instance of monad. But unfortunately, if you look at the prelude, or I mean, the base libraries, the definition is different a bit. It's not too bad. And I think I also by now lost track of what the current state is. But anyway, so but this is the idea. So that's what we want. And so first, some observations. Right. So I can define an fmap from state as given a function from A to B. I can turn a stateful computation that produces an A into a stateful computation that produces a B. I could do that ad hoc. I mean, with the definition of state, but I don't even have to. I can just use the bind. So what I do is I run the first computation, call the result A, and then apply my given function to it. And this definition doesn't at all depend on, I mean, I could do exactly this. I could write this line for my other examples as well. So maybe instead of state S, either, or instead of either string, or for this writer type, or for state, as I did here. So or as long, I mean, as soon as I have a bind with this type signature, I can just implement this. So that's the first observation. And that leads to the idea to spice this up and demand that functor is a superclass of this. And then we always have a canonical implementation of fmap. So, I mean, the idea would be in this case that we, I mean, in order to write an instance, in order to write an instance now, for example, for state, we would first have to define an instance for functor. And the idea would now be that in this instance for functor, state S. We just use this. And then of course we, oh yeah, because I hit it. So maybe I shouldn't. I mean, now I don't have to anymore. What is now? Yeah, okay. Normally I'm not supposed to give signatures, but I can add this instance sig extension to allow me to write signatures here. Okay, so that would be the idea. So functor is a superclass of monad, but we would always define the functor instance just by using this specific definition. Right, and the way it's actually done is there is a, in the base libraries, there's a, I can do that later. Sorry. Okay, and unfortunately, that's still not the end of the story. It's almost, it would have been the end of the story until like 15 years ago or so. Almost. But I right in the beginning of this of the lecture, I mentioned applicative. So this also now plays into this. And this I always find a little bit hard to motivate. Let's maybe start with, I don't know. I always find it a bit, maybe I can just write it down. I mean, we can define the following operator now. So let's say we have something with this complicated type. So we have a stateful computation. What's this now? Yeah, okay. So we have a stateful computation where the result type is a function from A to B. Sounds a bit weird, but bear with me. And then we have something, a stateful computation that has an A, and the idea is I want to turn it into a stateful computation with a B. And I can just write this down without knowing anything about state. So let's just call the first one F and the second one A. Is that a good idea? Maybe not. Let's call it MF and MA. So what do? I can first execute this stateful computation. I call the result, which is a function F. Then I execute this stateful computation. And I call the result A. And then I just apply the function I got to the result I got to get a B. And notice that we don't have any, I mean, that the state doesn't appear here anywhere, or the get or the put. All I'm using is the bind and the pure. Right, and this now hopefully motivates the final definition. So there is another class. And that's called applicative. Oh yeah, and one more thing. Right, this thing here. I can now, I don't even need to bind. Now that I have this thing, and I don't know what it's pronounced, app, I think. So I can also do this with this app. So I can do pure F X. Why do I get something here? Yeah, because I'm just defining it, idiot. Okay. So the point is I can already get this F map just with having this operator. I don't even need the bind. Okay, and this is now how class applicative is defined. So applicative has functor as as a superclass. And applicative actually has the pure. And it has this app operator. Sorry. MA to MB. Okay, and then monad is defined as superclass applicative. For monad, I think, is it still called return, or is there? Yeah, I think at the moment, do we know who we're
Yes,
talking
it's
about?
the
Okay.
correct.
Yes.
I mean, we will eventually be removed. It's not
Yes.
going to change names.
Yeah, so okay, but at the moment it's like this.
Yeah.
Right, so that's now the full story, I think. But morally, it's still sort of like what I said in the beginning. So a monad has this return and bind. And then it turns out once we have this return and bind, sorry, the pure and bind, or pure or return. Return is just another name for pure. So once we have this pure and bind, you can just define this app operator like we did here, using just pure and bind. And using this, you can also define fmap. So basically, once you, I mean, the like this bind is always the bind and the pure come first, basically. And once you have them, then you can just define fmap for functor and this diamond operator for applicative. And so you never basically write code here. So this is always uses this definition, which actually has a name. So this is normally called, what is it? App. Is it app? Yeah.
Yes, app or apply.
Right. But I think in the
Yes, the name it's pronounced apply.
oh yeah, right.
Yeah.
Right. So that's actually called app. And this thing here, sorry, that is called lift m. But just for, I mean, for arbitrary monads, so A to B state as A state as B. I mean, with this definition, let's see, pure F or app. Okay, fine. And I could write it like this, I suppose. Okay, and then once we have, and this is basically, as you see, the app and the lift m. I mean, the lift m only uses app, and the app only uses bind and pure. And then normally the way it goes is if you discover a new monad, you first define this bind and the return or pure, and then you can just write the functor instance by using lift m. And you can write an applicative instance. I mean, pure is pure, or pure is return, and this app is just that. So that's normally how it's done, and that's a bit unfortunate, but it will become, so it's a bit of boilerplate. But there are some techniques to remove that. But anyway, the end of the story is, I mean, this is called a monad. And if you have a monad, you automatically, more or less for free, have functor, and automatically, more or less for free, you have applicative. Okay. And now I think I can just remove all of this. And so now I can demonstrate how that would be done for state. So I mean, this definition that is basically the one from the standard libraries. So the way this would now go, if I this part here, now I want to turn state into an instance of monad. So the way I would do that is, I mean, I need to make it first a functor state s. Then I must turn it applicative. And finally monad. Right. So then I would take this definition for bind that goes to the monad part. Then I need, then the definition for this here I don't need, because that is just defined for arbitrary monads. Then this pure goes into here. But now, yeah, because okay. Now I need, now it complains that doesn't have the, does it complain about probably that the app is not defined? Yes. So now I would just don't bother and just use this app, which is defined in the module from the BICE libraries control monad. So I don't have to write any code here. And for fmap, I also don't have to write any code because that's just lift m, which is also defined in the standard libraries. And now, right now it would compile, I think, and everything's good, and all my code still works. Or not. Why? Because I didn't save. Okay. So that's how it's normally done. So once, I mean, if you want to implement a monad instance for some type, I mean, you have to, because of the way these classes are set up, you have to simultaneously define functor applicative monad. And normally the way is, I mean, you do it like this. So for functor, you just use lift m. For applicative, the pure goes into the applicative class. And for this diamond operator or apply, you just use app, which is defined for any monad. And then the bind goes in here. And now it's not even complaining that I didn't define return. Is that already done, this proposal that you don't need to define return anymore?
Yes, if you define it, it will give you a warning.
Ah, okay. So I don't even need to, I just need the bind, basically. Okay, cool. Right, and that's monads. And as I mean, the question was already, can we use do notation? And indeed you can. So we introduced the do notation for IO as an alternative, if I mean to declutter the syntax a bit. And actually the do notation doesn't just work for IO, it works for arbitrary monads. So that means we can now revisit our examples. So maybe, so if I don't hide this stuff anymore, and actually now I don't even need this because that's just in the standard libraries, the monad instance. So if we maybe if I ask for information, I see that on maybe I see monad maybe. So that's already defined. Actually, for state, it's also defined, but not in the base libraries. It's in, I think, MTL or the other one. What's the other? Transformers. Right, and then, so this compiles, because that's already the monad instance. This bind is already defined in the prelude, basically, for maybe. And now I can write this here nicer instead with do notation. So here I can just write do up. Okay. Like this. And now now it looks almost exactly like it would in imperative language, and that still compiles. So again, do notation is just it's just a matter of syntax. It doesn't do anything. I mean, I think the parser, I mean, at a very early stage of the compiler, this already gets translated into the equivalent using bind. And I can do the same with either. I want to. I mean, this is exactly the same code. I think with writer, I don't do this. Auto would be a bit difficult because I didn't introduce a new type for that. Maybe I should have. Okay. So this also just works. Or not. Why must I? Why doesn't it work? Because I didn't delete these. So that's also for either. It's also in the prelude, so we don't even have to define it ourselves. And state. Now that I mean, that is, as I said, we could just import the right library and then we also wouldn't have to implement it ourselves. But now that we have, we can also rewrite this nicer using do notation. Why do I get all sorts of, I deleted too much. Okay. So this is nice. And finally, this applicative thing. We can also, using applicative, we can write this even cooler, like so.
Lars, I'm not sure if you want to go there, but if you see applicative as the function application at the functor level, it's like the types match perfectly and also the name. So you can think of applicative as a way to apply functions to functors or applicatives in this case.
Yes. So what one can actually do, and maybe you have to think about that, why that actually works, and recall that we have this dollar operator that is just another word for fmap. So this thing here I can just write like this using so-called applicative syntax. Which is, I think, really cool. But you have to think a bit about why that actually works. But if you look at the types of the definitions of fmap and of app, then you will see it works. And nicely, the nice thing is this doesn't just work for two arguments. I mean, it would also work for functions with more than two arguments. So yeah, one way to think of applicative is that you can map functions over like effectful computations. And I mean, what's also probably we don't have time to go into that either. But applicative, I mean, it's weaker. It sits between functor and monad, and so basically the difference is, or it's strictly weaker. So applicative, you can have side effects, but the result of one computation can't influence the side effects of another. So or can't influence what you do next. So we only really need bind if the result of one computation influences what we do afterwards. Like here. Here it does, because the result of the get influences what we put there. But is that a good way to say it? I'm not sure. But anyway, here we know in advance that we will label the left tree and we will label the right tree, without caring what the result of labeling the left tree is. So that is often, it allows this so-called applicative syntax, and it's also not by, this also explains somehow why this uses this $sign similar to function application, because one way it's sort of like a function application. And another way to try to understand functor and applicative is, functor basically means you can lift a function over, functions of one argument. You have a function from A to B, and you can lift that to functors. So then you can have it from FA to FB. And what applicative does is it generalizes that to functions with arbitrary many arguments. So pure is basically nullary functions only without arguments, and the app generalizes it to 2 or more arguments. So as soon as you have, functor, basically you can only lift functions with one argument. With applicative, you can lift functions with arbitrarily many arguments. And then monad has this special additional feature, this context sensitivity, that what you do later can depend on the results of what you do first. So that's the most powerful. In practice, most applicative functors are also monads. So often, the use of applicative is not so much that there's a difference, that in power, because normally the standard examples of applicatives, are all just monads. So the only reason why one would bother with the applicative instance at all is because you can then sometimes write things very concisely like this. There are, however, exceptions. So there are instances of types that are applicative but that are not monads. But I think we won't get to that. Right now we are almost out of time, and I don't know, are we at the point now where we can do projects, Robertino, Karina?
Yes, we are.
And okay.
Yes, we have the W01, which will be like the project that they can work in, like for the time that you want to give them.
Right. So the point is that I'll be on vacation for the next 2 weeks. So there won't be lectures in the next 2 weeks. So the idea is that instead you work on a project. So we will share that right on the repo. And then you have the next 2 weeks in principle, or do you want, should we only say like 1 week or 1.5 weeks so that you have time to look over it? How should we do this? Or should it be the next 2 weeks?
We could give the most of the time, and yes, like maybe a few days before the 2 weeks. So in the last few days, we can look over them and get you up to date with everything. Almost 2 weeks.
Yes, almost 2 weeks.
Yeah.
Okay, almost. So the idea is that, this is basically now, this is a good point. Every introduction into Haskell should at least cover monads, which we now did. And as I said, if you find this confusing, I try to motivate it with many examples. But as I also said in the beginning, it's like most people that learn Haskell find monads the most difficult thing to understand. So after monads, it's just a walk in the park. But they are very useful and they are everywhere in Haskell. So it's, but you don't have to worry if you don't understand it right now. That comes with familiarity. So it normally takes a while until it clicks. Took a while for me as well. But they are very powerful. But anyway, so this is now like, you can consider this now as an introduction into Haskell, like beginner's level. Of course, there's much more to say about Haskell, but I would say this is like an intro level now. And so you are definitely now able to do like interesting stuff, like work on a project. And we will, I think Niamh and Anderson will discuss maybe next week or so. But our plan is actually to pivot from, after my break, after my vacation, so in 2 weeks, we won't do much more with Haskell and instead dive into smart contracts on Cardano. So if you, it would be nice, of course, if you revisited what we did about Haskell now and did all the assignments and of course work on the projects. But if you, you basically can have a fresh start in 2 weeks, because then you won't need much Haskell anymore, and we will dive into like practical stuff on the Cardano blockchain and writing dApps and so on. So yes. Anything else I should say, Robertino? Or?
No, I think that's it. Like, we will be available for them, of course.
Yes.
So if they have any questions during these 2 weeks that they have to get to the project, we will be there for them. And I'm not sure if you have any questions right now. Okay.
Okay. Then I hope you will enjoy working on the project. Often it's, I always find it's much easier to learn something if you actually have a goal. So if there's something that interests you and that is fun to work on, then it's easier to learn things if you have this goal in mind. So hopefully this will be good for you. And then, as I said, in 2 weeks, we'll dive into Cardano and do blockchain stuff mostly. Okay, then thank you very much. And if there are no further questions, then I'll talk to you in 2 weeks. But Karina and Robertino and Antonio will be around for your questions if you have any.
Okay.
Okay, then.
Yes.
Thank you, Lars. Bye, everyone.
Thank you.
you.
Thank you.
Bye.
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 Thank you.